Welcome friends, I am Dr. Rajesh Singh and this is part 4 of the video Solution to Exercise 4.2 of the book Bartle and Sherbert. In part 1, 2 and 3 I have solved from question number 1 to question number 12. In this video I will solve question number 13, 14 and 15 of the exercise 4.2. So let's start with question number 13. So in question number 13, we have been given two functions f and g, where f is defined as fx is equal to x plus 1 and gx is equal to 2 if x is not equal to 1 and g1 is equal to 0. So we have in the a part of this question, we have to find limit x tends to 1, g of fx, and then we have to compare this value with the value of g of limit of x tends to 1 fx. So given is fx is equal to x plus 1 for all x in R and gx is equal to 2 if x is not equal to 1 and 0 if x is equal to 1. So this is how g is defined. So let us first find limit x tends to 1 g of fx. So first we will find g of fx for any x. So g of fx is equal to g of x plus 1, which is equal to 2 if x plus 1 is not equal to 1 and 0 if x plus 1 is equal to 1. So that is 2 if x is not equal to 0 and 0 if x is equal to 0. So this is how g of fx is defined. So g of fx is 2 if x is not equal to 0 and 0 if x is equal to 0. So if I will, so clearly limit x tends to 1, g of fx is equal to 2. Also limit x tends to 1, f of x is equal to limit x tends to 1, x plus 1, and this is 2. So g of limit x tends to 1, f of fx is equal to g of 2 and g of 2 is 2. So here we have got limit x tends to 1, g of fx is equal to g of limit x tends to 1, f of x. Now let us see the part 2 of this question P. So in part 2 we have to find limit x tends to 1 f of gx and compare its value with f of limit x tends to 1 gx. So let us first find f of gx. So f of gx is equal to f of 2 if x is not equal to 1 and f of 0 if x is equal to 1, and this is 2 plus 1 if x is not equal to 1 and 0 plus 1 if x is equal to 1. So this is your 3 if x is not equal to 1 and 0 if x is equal to 1. So here limit x tends to 1, f of gx is equal to 3. Now let us try to find limit x tends to 1 gx and then we will find f of limit x tends to 1 gx. So limit x tends to 1 gx is equal to 2. So f of limit x tends to 1 gx is equal to f of 2, which is 2 plus 1 3. So again in this case, limit x tends to 1, f of gx is equal to f of limit x tends to 1 gx. So this completes our question number 13. Now we will move to question number 14. So in question number 14, we have been given a function f from a to r and c is cluster point of a. We have been given that limit x tends to c f exists, and mod f is defined as mod f of x is equal to mod of fx. We have to show that limit x tends to c mod f is equal to mod of limit x tends to c f. So let us start with the solution. So mod of fx is defined as mod of fx for all x in a. To show limit x tends to c mod f is equal to limit x tends to c f. So let limit x tends to c f equal to L, because it is given that limit x tends to c f is existing, so we can assume it to be some real number L. So we will show that limit x tends to c mod f is equal to mod L. So claim limit x tends to c mod f is equal to mod L. So this we will show. So let epsilon greater than 0 be any real number. Then we have to find some delta such that mod f minus mod L is less than epsilon whenever 0 is less than x minus c less than delta. Since limit x tends to c f is equal to L, so there exists delta greater than 0 such that 0 less than x minus c less than delta implies mod fx minus L is less than epsilon. So this is our star. Now consider mod of mod fx minus mod L. So this I can write as mod, by definition of this is mod of fx minus mod L. Now using reverse triangle inequality, this is less than equal to mod x minus L. Using reverse triangle inequality. And what is the reverse triangle inequality? So reverse triangle inequality says mod of mod a minus mod b is less than equal to mod a minus b. So this is reverse triangle inequality. So I have used this here. And this is given to be less than epsilon whenever 0 is less than x less than c. So then mark it as double star. So from star and double star, it follows that 0 less than x minus c less than delta implies mod of fx minus mod L is less than epsilon. Hence, by definition of limit x tends to c, mod f is equal to mod L. So this we have proved, and mod L is nothing but limit x tends to c f x. So this is what we had to prove. So this completes the proof of question number 14. Now let us start with question number 15. So in question number 15, we have to show, we have been given that f is a function from a to r, c is a cluster point of a, and fx is given to be positive for every x in a, and we are defining the function root f as root of f of fx is equal to root of fx, and we have been given that limit x tends to c, f exists, and we have to show that limit x tends to c, root f exists. So this we have to show. So proof. So this is similar to proving that limit x tends to c, root x is equal to root c. So this is the proof of this will follow on the same lines to the proof of this. So given is fx is greater than equal to 0 for all x belonging to a, limit x tends to c, f exists, and root of fx is equal to root fx for every x in a. To show limit x tends to c, root f is equal to root limit x tends to c, f. So let limit, because it is given that limit x tends to c, f exists, so we will assume that it is equal to some number L, where L belongs to, L is some real number. So this we have assumed. We have to show limit x tends to c, root f is equal to root of limit x tends to c, f. So for this, what we will do, we will take any arbitrary epsilon. So let epsilon greater than 0 be any real number. So we have assumed epsilon to be any real number. Now we will show that root of f minus root of L is less than epsilon whenever 0 is less than x minus c less than delta for some delta greater than 0. So now we will proceed in two cases. So case 1, L is equal to 0. Consider root of fx minus root L. So this is nothing but root of fx minus 0, and this is because root fx is positive, so this is equal to root fx. So mark this as a. So this is our a. Now since limit x tends to c, f of x is equal to L, so for above epsilon greater than 0 there exists delta 1 greater than 0 such that 0 less than x minus c less than delta 1 implies fx minus L is equal to 0. So fx minus fx, this is equal to 0. So fx minus 0 is less than epsilon square. So instead of epsilon, I am taking epsilon square here because I need this to be less than epsilon. So then, so let us mark this as b. Then for delta equal to delta 1, using b in a, we get for 0 less than x minus c less than delta root of fx minus 0 is less than epsilon. So we will put epsilon square here. This is less than epsilon more because fx is less than epsilon square. So root fx is less than epsilon. So this is true, and this is by definition of limit. Hence limit x tends to c, root f of x is equal to 0, which is limit x tends to c fx and root of this. So in case 1 we have proved this. Now let us proceed to the case 2 when L is not equal to 0. So case 2, L is not equal to 0. So since fx is greater than equal to 0 for all x belonging to a, so this implies L is strictly greater than 0. And since limit x tends to 0, fx, which is L, is strictly greater than 0, so there exists delta 2 greater than 0 such that fx is greater than 0 for all x belonging to c minus delta 2 to c plus delta 2. So since limit x tends to c, fx is greater than 0, so we are able to find a delta 2 greater than 0 such that fx is greater than 0 for every point in this interval c minus delta 2 to c plus delta 2. And which theorem we are using? We are using theorem 4.2.9. So this is the result that we are using. So you can see if limit x tends to c, f is greater than 0, then there exists a neighborhood v delta c of c such that fx is greater than 0 for all x in a intersection v delta c and x should not be equal to c. So we have to add this make it intersection a and x not equal to c. Now because fx is greater than 0 for every x in this, so what we can do, we can choose some a greater than 0. So there exists a greater than 0 such that fx is greater than a for every x in v delta c intersection a and x not equal to c. So mark this as a. Okay, a we have already taken, so mark this as a1. So we have marked this as a1. Now we have to show that limit x tends, what we have to show limit x tends to c, root f is equal to root L. So this is what we have to show. So we will start with root f minus root L. So consider root of f x minus root L. So this is equal to root of fx minus root of L. Now what I will do, I will multiply and divide by root fx plus root L. So I will get this. This will become fx, or right, let me add one more step. So I am multiplying and dividing by root fx plus L. Root L. So after multiplying and dividing, now this is equal to fx minus L upon root fx plus root L. So now this I can make it less than epsilon using limit, but I have to make this less than some constant. So 1 by this of less than some constant. So this term is positive, this term is positive. So I can remove the modulus. So this is equal to 1 by root fx plus root L fx minus L. So what I will do, this is less than a. So if I will this is greater than a, so if I will replace this by a, then this number will become bigger because I am decreasing the denominator. So this is less than 1 by a plus root L fx minus L. So I want this to be less than epsilon, so this should be less than epsilon a plus root L. So mark this as a2. Now since limit x tends to c, fx is equal to L, so given for above epsilon greater than 0, there exists delta 3 greater than 0 such that 0 less than x minus c less than delta 3 implies fx minus L is less than epsilon a plus root L. So this thing is true whenever, so this is true whenever 0 is less than x minus c less than delta 2 using a1. So we have used a1 here. So this thing is holding only when 0 is less than x minus c less than delta 2, and this is true using A1. Now mark this as A3. So now we want A2 and A3 to hold together for the same delta. So what we will do, we will take let delta equal to minimum of delta 2 and delta 3. Then from A2 and A3, 0 less than x minus c less than delta implies there are two things. First, root of fx minus root L is less than 1 upon a plus root L mod fx minus L, and second, fx minus L is less than epsilon upon a plus root L. Now combining these two results, what we get? So this implies 0 less than x minus c less than delta implies root of fx minus root L is less than epsilon. Hence, limit x tends to c, root of fx is equal to root L, and root L is nothing but root of limit x tends to c fx. So in either case, we have shown that limit x tends to c root of fx is equal to limit x tends to c fx. Hence the result. So this proves question number 15. Now I've missed question number 11 D part in part 3 video, so I will solve that question. So let me solve question number D. So I will solve only this here, other are solved in part 3 of this video. So solution 11D. So to show limit x tends to 0 root x sine 1 by x square. So we will show that this is 0. In this case, limit exists and it is equal to 0. So we will show this. So for this, define let fx is equal to root x sine 1 by x square for all x greater than 0. So this way, because this root is defined only when x is greater than equal to 0, and this is defined when x is not equal to 0. So simultaneously both are defined whenever x is strictly greater than 0. So this we have assumed f is this. So we have to show that limit x tends to 0 fx is equal to 0. So for that we will choose any epsilon greater than 0. So let epsilon greater than 0 be any real number. Then to show there exists delta greater than 0 such that 0 less than x minus c less than delta should imply fx minus 0 to be less than epsilon. So for this, what we will do, we will start with mod fx minus 0 and we will try to get some condition on x minus c, then we will be able to find this delta. So consider mod fx minus 0. So this is nothing but root x sine 1 by x square minus 0, and this is root x sine 1 by x square. So now using modulus property, this is root x sine 1 by x square. Root x is always positive because this is a positive square root of x. So we can write it like this, and sine 1 by x square is less than equal to 1. So I can use this inequality less than equal to 1 and I can replace this by 1, since sine 1 by x square is less than equal to 1. Now I have to this is root x, and I have to get this form. So what I will do, okay, c is given to be 0, so make it 0 here. So I have to get, if I will take some delta such that 0 less than x minus 0 less than delta should imply this. So what I will do, I will take let delta equal to epsilon square, which is greater than 0, then 0 less than x minus 0 less than delta implies, because x is given to be positive, so I can take this model out. So x is less than epsilon square, and this implies root x is less than epsilon. I can take square root because both are positive, and so this inequality is not reversed, so we can take this square root on both sides. Now root x is less than epsilon, so from this what we get, this implies, because this is fx minus 0 is less than root x, and root x is less than epsilon, so this implies fx minus 0 is less than epsilon. So hence limit x tends to 0, fx is equal to 0, that is limit x tends to 0, root x sine 1 by x square is equal to 0. So this completes question number 11 D part. So we have solved all the questions of exercise 4.2. In next video, I will solve questions from exercise 4.3 of the book Bartle and Sherbert. Till then, stay tuned and subscribe to our YouTube channel for more updates. Thank you.